Hello and welcome to another video on orbital mechanics, going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, 4th edition, and we're going through some theory. Now in the last video I talked about the restricted three-body problem, and I have it here. We went through the setup and deriving these three equations for x, y, and z in the three-body problem, and we said that we could use those to figure out some interesting things. And just a correction, there should be a negative here and here, here. So that was a mistake. I'm going to go forward now, and we're going to go on to Lagrange points. And to get to the Lagrange points, which are points in an orbit of a three-body orbit, where you're the small spacecraft, you're the point where there is no relative difference, changes between you and the planets. So that means that your velocity in any is completely zero and your acceleration is zero relative to the moving frame. So these are the equations that we are starting with. There's the x, there is the y, and there is the z, which we derived in the last video. So go watch it if you didn't watch it. If you didn't understand it, let me know and I'll maybe do another one or answer the question. And when we set those to zero, it becomes slightly simpler. So we have our x a bit simpler, our y a bit simpler, and our z ends up very simple and equal to zero. So that means that z is zero if these are both greater than zero, which they are. So we know that it's on the z plane. All of our Lagrange points are on the z plane in our moving frame. Now over here we have some additional useful things that we've worked out over the last couple of videos. So we have pi equals m1 over m1 plus m2, pi 2 equals m2 over m1 plus m2, and actually pi 1 plus pi 2 equals 1. And that can be figured out by just adding those together and watching things cancel. They do add up to 1. These are ratios, really. And we have the angular momentum equals the square root of our gravitational constant for the spacecraft divided by r12 cubed. And this here, n of ne equals mu of ne over the gravitational constant. And if we put that into here, we get mu1 equals pi 1 mu, and mu2 equals pi 2 mu. So these are all going to come in handy to simplify our equations. And so the first simplification, after setting everything to zero and getting these new equations, takes us to this for x and this here for y. And actually y has it's been cancelled out in the end, so it's not even in the equation. And just some other helpful stuff here as well. If we take those as simultaneous equations, and they do look a bit mad, you will get that r1 equals r2 equals r12, and that is evident. If you look at it, you see this here coefficient would be in here, this coefficient would fit in here, and this x would be next to the 1. So if you said x was 1, and all of this was equal to 1, and all of this was equal to 1, it would then match this equation. And so if you can assign 1 to all of those and then find and replace, you get out some interesting things. Like, for instance, this, I think, comes out to be 0, which means that's 0, which means they are equal, right? So things like that. It just works out that these are all equal, and there's no way getting around it. Keep trying to work things out in there, and things always end up equal. So that's that. So now that we know they're all equal in this condition that we've set ourselves in, we can go back to our original vector equations here. So this is from the last video. R1 equals x minus x1 for the I vector, and plus y j vector, and for the R2 it's x minus pi 1 r12 I vector plus the y of the j vector. And we have, remember, we have these these ways we can twist and change our pi1 to be pi2. So we're not limited to this basic equation. But when you expand these things out to get things in the format that everything is as fewer terms as possible, and we're going to get pi2 r12 into our equation. And when you just realized there's a mistake here, because there's a mistake in the book actually. This should be r. Sorry. When you do that out, you get to r12 squared, because that there squared and rooted is the magnitude. So that's the magnitude, and then everything's squared. So this makes sense. So r12 squared, x plus pi2, r12 squared plus y squared, etc. And if we equate the right-hand side with the right-hand side and simplify, we get this. So the y's disappear because they're both on both sides. It comes to this. If you take this and put it back in here, you get this. So this is our x and y position for Lagrange point 4 and 5. And we have one that's on top and bottom. And what this ends up being is, let me draw it for you. I'm just going to draw a little one. That's Earth, for example. That's the moon. And it ends up being, yeah, L4 and L5, like that. And these three, that's your R1, that's your R2, and that's your R12, are all the same. It's an equilateral triangle, which is great. Looks awesome. Right, moving on from there. So we have two Lagrange points. There's three left, L1, L2, and L3. And going forward with that, to get those, we set y equal to 0. Now, don't know why that was ever done, but it works. You know, it's obviously a way to simplify down to a solution. So probably there is no other solutions. So y equals 0. When we do that, we get r1 equal to, and z is still 0. R1 is equal to x plus pi2 r12 I, and just I, and then r2 is same sort of business. And then so we know that the magnitude is just that amount there, because it's on a single vector. So when we take those values and put them back into our equation here, very important, this one, for x, out will come a fairly complicated mess here. And we also need to, use these to simplify into only these terms. So that's what's going on here. This angular momentum is getting replaced by this, and this R1 is being replaced by, won't be using this one. This only applies to L4 and 5. Yeah, when you use all these components to simplify and you use these definitions of R1 and R2, this is what comes out, and it equals to 0. Now this is not solvable analytically, so what is done is it is simplified by taking this xi equals x over R12, and you can check this with some basic formulas. If you plop that in so I did x equals xi times R12, and here and here, here and here, and here, and then the R12 basically cancels, right, across the whole thing, right? It is consistent and it does cancel. And you end up with this, and we say f of pi2 comma xi equals that. And this is also not solvable, but if you put in a range of pi2 and xi, you get this graph. And this graph is awesome because it shows us where our L3, L2, and L1 roughly land for different values of pi2. It's not exact, but we can use it to get a starting point. So if our pi2 was, say, here, our starting point for L3 would be here, and L2 would be here, and L1 would be here. and we would put those values into our equation, and hopefully we'd come to something close to 0. And then what we would do is try different values until we got an answer that is 0. And when I say try different values, there is a method for trying better values so that you don't spend your rest of your life trying values. It's called the bisection method, and it's one of many goal-seeking methods that are available, but it's one of the simplest ones. And I will cover that now in MATLAB.
So this is MATLAB with example 2.16 from the book, and here I have the Earth, the Moon, and the distance from the Earth to the Moon. So there's the Earth, the Moon, and R12, and R12 is known, so we can get pi2, which is m2 over m1 plus m2, and then the length L, the Lagrange point for Lagrange 4 and 5 is R12 divided by 2 minus pi2 times R12, and the y position is the square root of 3 divided by 2 times R12. And then we can create our vectors there, this one, and then for L1, 2, and 3, we can use our bisection method for different ranges within the graph that I showed you, and this results in, then multiply by R12 to get your final position on the x-axis, so 1, 2, or 3. Now the bisection method works by taking the positions given, taking the midpoint of those, evaluating both points, and then depending on which side the point lands, if it's greater or less than 0, we know which one was effectively a boundary, so then we can choose the other point to make our new limit, and then we can repeat the process again. And and that's it. That's the bisection method there. And that does it for n times. Now n is the ceiling of this equation. Now if you have this to start with, which is the absolute value of the upper limit minus the lower limit divided by 2 to the power of n, is less than the error margin that we're looking for, right? And that makes sense, right? Every time we do this, we halve the size of the search area, roughly. So it's roughly this value that will come out being smaller than epsilon. And then if you use logarithmic identities to rearrange this, you come out with this. So that's what n eventually equals. And I think the book comes out with like 18 or something. So, but it depends on what you start with to get to that value, right? So roughly about 20 in this case. And that's it. I run that. You can see these values down here do match what's in the book here for that example, and then actually 2.46 question is basically the same, but it's for the sun and the earth and the moon, I think, and we will do that in the next video. Right, thank you. If you have any questions or you think I've made a mistake, leave them in the comments below. Bye bye.